Imagine standing in a city like Tokyo or San Francisco, where the very ground beneath your feet could start to tremble at any moment. For centuries, earthquakes have been one of nature's most destructive forces, devastating communities, collapsing buildings, and claiming countless lives. But today, thanks to incredible feats of engineering and cutting-edge technology, many of our modern structures can not only survive but thrive in the face of these violent tremors. This is the story of how human ingenuity turned nature's fury into a solvable and fascinating challenge. Let's travel back in time. In the early days of construction, buildings were designed with one primary goal: strength. Rigidity was seen as the ultimate defense. But when earthquakes struck, this philosophy proved deadly. Rigid structures couldn't bend, they could only break. The devastating 1906 San Francisco earthquake and the 1923 Great Kanto earthquake in Japan were tragic wake-up calls. These disasters forced engineers and architects to confront a terrifying reality and ask a revolutionary question. What if buildings could move with the earth instead of fighting against it? This single question ignited a revolution in civil engineering, changing our skylines and saving lives forever. One of the most transformative ideas to emerge from this new way of thinking was base isolation. The concept is brilliant in its simplicity. Instead of anchoring a building directly to its foundation in the ground, engineers decided to decouple it. They essentially placed the entire structure on a set of flexible bearings, often made from layers of rubber and steel. These are called lead rubber bearings. When the ground shakes, these bearings act like a suspension system in a car, absorbing the seismic energy and allowing the building above to sway gently, almost as if it's floating. The ground moves violently, but the building itself moves far less. This technology has been proven to reduce the stress on a building's structure by up to 90%. It's no wonder that base isolation is now a standard feature in critical buildings like hospitals, data centers, and museums, especially in places like Japan and New Zealand, which were pioneers in its widespread adoption. Now let's look up, way up. Have you ever wondered how super tall skyscrapers, those glittering giants that pierce the clouds, manage to stay standing during earthquakes or even powerful winds? The secret often lies in a remarkable device called a tuned mass damper. Imagine a giant, heavy pendulum, sometimes weighing hundreds of tons, suspended near the top of a skyscraper. When the building starts to sway in one direction, this massive weight swings in the opposite direction. This countermotion effectively cancels out much of the building's movement, stabilizing the entire structure. The most famous example is the 660-ton golden sphere inside Taipei 101. It's so impressive that it's become a tourist attraction in its own right, a visible testament to the invisible forces at play. Tuned mass dampers are the unsung heroes that allow our cities to reach for the sky safely. But what happens to the materials themselves during an earthquake? Traditional steel can bend and concrete can crack, often requiring extensive and expensive repairs after a seismic event. This is where the next wave of innovation comes in: smart materials. Picture this: a metal that can be bent completely out of shape and then, with a little heat or on its own, magically return to its original form. This isn't science fiction, it's the reality of shape memory alloys. When used in the joints and braces of a building, these advanced materials can absorb immense energy during an earthquake by deforming, and then revert back to their original shape afterward. This incredible property not only protects the building from catastrophic failure, but also drastically reduces the need for post-earthquake repairs. While still relatively expensive, shape memory alloys represent a leap towards creating truly resilient, self-healing structures for the future. Of course, we can't talk about construction without talking about concrete. By itself, concrete is strong under compression but brittle and weak when stretched or bent, a fatal flaw during an earthquake. To overcome this, engineers developed innovative reinforcements. Instead of just standard steel rebar, they began using advanced materials like fiber-reinforced polymers, or FRPs. These composite materials are incredibly strong and lightweight, and they can be wrapped around concrete columns to give them the flexibility they need to survive. At the same time, engineers began designing structures with ductility in mind. A ductile frame is designed to bend and deform in specific, controlled ways without breaking, dissipating the earthquake's energy safely. This is crucial for preventing the kind of sudden, catastrophic collapse that costs lives. You'll find this technology in everything from our bridges and tunnels to our tallest towers, and it's a cornerstone of seismic retrofitting projects that make older buildings safer. In regions prone to earthquakes, especially after a disaster, time is of the essence. Rebuilding homes and infrastructure quickly is critical for a community's recovery. This need for speed has driven another powerful innovation: modular and prefabricated construction. Instead of building from scratch on-site, entire sections of a building, or modules, are constructed in a factory under controlled conditions. These modules are designed from the ground up with seismic resilience in mind. The uniformity of the components allows for much stricter quality control over the structural integrity. Once completed, they are transported to the site and assembled like giant building blocks. This method is not only incredibly fast, allowing emergency housing to be deployed within days, but it also ensures a high standard of safety. Countries like Chile, Nepal, and Turkey have embraced this technology to rebuild faster and stronger after devastating quakes. The adoption of these life-saving technologies isn't just a choice. In many parts of the world, it's the law. Nations that sit on seismic hotspots, like Japan, Chile, New Zealand, and parts of the United States, have embedded earthquake-resistant design into their building codes. In the end, earthquake-resistant building innovations are so much more than just engineering marvels. They are lifelines. They represent our incredible capacity as a species to learn from disaster, to adapt to our environment, and to build a safer future. As our cities grow and our world faces new challenges, the work of these engineers and scientists will become even more vital in protecting communities and future generations. So the next time you walk into a skyscraper or cross a modern bridge in a seismic zone, take a moment. Remember that beneath the sleek facade and polished floors lies a hidden story of science, sacrifice, and survival, a testament to human ingenuity standing firm against the shakiest of grounds. Thanks for watching. If you found this story of innovation inspiring, don't forget to like this video and subscribe for more deep dives into the amazing world of science and engineering. Stay curious,